Everyone, this video has us diving into the physics concept known as projectile motion. It is the physics that describes any time you think of something like a cannon going off or someone throwing a ball off a cliff, that typical parabolic curve. So in this video, we're going to introduce this idea and, more importantly, how we approach solving these problems. Projectile motion seems pretty complicated, and there can be a good amount of math that you have to work through. Several equations, maybe a couple different unknowns, but the basis, the underlying concept is pretty simple. Projectile motion is just something that's moving horizontally, as well as something that's moving in a free fall type way. And we've already looked at both of those things. So projectile motion is just the combination of these two things. All right, for this slide, at some point you will want to copy down the diagram. You could hit pause or maybe wait until we finish up, because we are going to be adding more things, but this is going to be a crucial diagram for you to have drawn. What I have is just some person who is standing at the top of a cliff or maybe standing on a building, and they're throwing a ball. And they're going to throw the ball perfectly horizontally. We're going to ignore air resistance, anything like that that might get in the way. And we're just going to think of how this ball is going to move from when it's thrown. Obviously, if you're throwing a ball, you start off with the ball in your hand, and then you accelerate it, right? You throw it, you hurl it with your arm, moving in a obvious tossing pattern. But we're really just going to look at right when the ball has left the person's hand. Okay, we're going to say it's been released again horizontally, so it has some initial velocity in the x direction. That's what that blue arrow represents. Well, after it's left the person's hand, that individual is no longer throwing the ball. All right, they're no longer pushing on it. So once it's left the person's hand, this horizontal velocity, there's nothing to change it. There's nothing to increase its horizontal motion, nothing to decrease it, again, if we ignore things like air resistance. Well, if there's nothing to change that horizontal motion, that by definition means it has no horizontal acceleration. So in the beginning, it has a velocity horizontal vector like this. A moment later, well, it shouldn't change. Another moment, still shouldn't change. Another moment, another moment, another moment. All of these velocities in the x direction should be constant. Because again, right after you've thrown the ball, right after you've released it, there's nothing to make it speed up or slow down. So these arrows should all be the same length, representing the same speed or the same velocity. Now, I know what you're thinking. Well, geez, of course the ball isn't just going to move in a straight line. It's going to start falling down, and you're absolutely right. Here's where the free fall portion comes into play. The moment you release this ball, the acceleration due to gravity is going to start pulling it, start accelerating it downward. It started off completely horizontally, so no vertical velocity. But right when it leaves the hand, oh, sorry, I forgot an arrow over there. Right when it leaves the hand, oh, there's a Vy. And we'll call that Vy number 1. That initial or that vertical velocity it has right at this spot. Well, some other time later, remember, gravity is an acceleration, which means it causes velocity to change, increasing in the downward direction. Here's the velocity in the y direction another moment later. And another moment, and another moment. You get the idea. As the ball is moving to the right, gravity causes it to accelerate, which means it gets a larger and larger and larger and larger downward velocity. And this adds up, if you think of these as vectors, to the classic, let's see if I can draw it freehand, it won't look too great, parabolic motion of that ball. When you throw something off a cliff, it follows this curved path. This is really just the combination of these two vectors. The vertical velocity, which is staying constant, and as the vertical one gets bigger and bigger and bigger, the arc should be curving steeper and steeper downward, because you have a larger and larger downward component. This is our key diagram for projectile motion. Here's kind of a nicer one. You don't necessarily have to draw it again, but the ball itself follows the solid green. Okay, so first it's going like this. Then at this moment here, this way. At this moment, it's going like this. This moment, it's going like this, and so on. You might be thinking, well, why are we caring about this x velocity and this y velocity if really it's following this parabolic path? Well, we have equations already for things moving horizontally and things moving vertically. That's what we spent the last couple classes going over. And also notice what I just drew in red. The direction is constantly changing. These arrows are getting steeper and steeper, arcing more and more down. We talked about equations in the x direction. We talked about equations in the y direction. We have not written an equation for the, mostly x and a little y direction, or the kind of 50-50 x, 50-50 y. We only have this one and this one. Well, since this motion of whatever our projectile is has a horizontal component and a vertical component, we can use those equations. You should copy down this table. This is our main resource. These are sets of equations. You could just make a simple t-table. But let's make sure we understand what's happening. In the x direction, that's what I want to focus on first. As we said before, there is no acceleration. Once you've thrown the ball, and it doesn't just have to be throwing a ball, once you've fired the gun, once you've launched that arrow from a bow and arrow, if you're no longer pushing on it, and if we're ignoring air resistance, that horizontal piece needs to stay the same, which means you have a super simple equation. If your horizontal velocity isn't changing, it's just going to equal the distance divided by the time. Okay, displacement over t. I have it rewritten, but this is the same equation. So in the x direction, projectile motion is simple. In the y direction, though, things are accelerating. It's falling. So you have an acceleration of negative 9.8, and here are, once again, those free fall equations. We have these three. So we can look at any object as a projectile, even though it's looking like it's going through this complicated motion, both in the x and in the y. All we have to do is use the equations for x and y, because we can break any of these things down into components. For example, let's say you were trying to find this velocity right here. Well, if you could know, or if you could figure out Vx, and it's constant, if you could figure out Vy with one of these equations here, this is just the hypotenuse of a triangle. So what I have in red, that's like the velocity of the object, the resulting velocity. Well, that resulting velocity is just a Pythagorean theorem of the horizontal velocity at that moment added vectorially, so adding with triangles, to the vertical component. So if you need to figure out the velocity of a projectile, even if it's at this weird angle, you figure out the velocity it has in the x direction, which is usually staying the same, and you figure out the velocity it has in the y direction, probably using one of these equations. You do the Pythagorean theorem to solve for the velocity of the object. That's what we're going to be practicing the next couple days. It isn't just for things being launched off of a cliff. You don't have to copy down this diagram. There's a lot going on. This is an example of maybe you're kicking a field goal. So instead of it just being tossed horizontally in the beginning, maybe in the beginning it's launched at some angle. But we can still just break that down. The blue in this picture has the velocities in the x. Notice it's not changing. Once it's kicked, that velocity in the x is staying the same, and you're launching with some velocity in the y. And just like when we saw problems when you throw an object up into the air, because it has this downward acceleration, this negative 9.8, it's going to have a decreasing upward arrow till it has 0, then it's going to speed back up. But once again, you could figure out any of these purples, by knowing Vx squared at that point, Vx squared, plus Vy squared. Couple more things. You may come across, whether it's a problem that I'm giving you, a problem from the textbook, a problem from an AP question, you might see something asking for the impact speed or impact velocity. You might see both. Or you might see a phrase, the speed when it hits the ground. Or it's asking, calculate the speed or velocity upon impact. You gotta get used to these phrases and what it does mean and what it doesn't mean. They're always asking about the speed or the velocity just before impact. So if you imagine, here's the ground. If you imagine something falling as a projectile, these words, these phrases don't mean after it's hit the ground and it's been sitting for a while. They don't mean that. They say, what's that velocity like right here, that split second before it hits the ground? All right, no one's trying to trick you. The answer to any of these math problems is never going to be, oh, haha, it's 0 because it's hit the ground, and now it's not moving because it's in the ground. They're always asking that speed right as the object is hitting the ground. Okay? Don't think, oh, it must be 0 because it's hit the ground and that's stopped. That's not what they're referring to. All right? You don't have to copy this down, what's in red. Last thing I see a couple common mistakes when people first try approaching these projectile motion problems. Let's say you're tasked with finding this velocity. So again, I don't know, you have a person who's throwing a ball, and they say, find the velocity right here when it's such and such height above the ground. People do something that is totally incorrect physics. I understand their reasoning, but it doesn't work out. They say, okay, we're trying to find this velocity. Well, I know the x direction. I know the y direction. So the velocity here is distance over time. Well, if I know x, if I know y, that's going to be x squared plus y squared divided by the time. Bing, bang, boom, I'll have my velocity. That is totally incorrect. When you're trying to find these velocities, you must use the velocity vectors. You have to, for two reasons. This approach, just looking at the x direction and the y direction, that would be giving you, if you did the triangle, this. That's your triangle right there when you do x squared plus y squared. But notice, the ball is not traveling that direction. It's not traveling that path, I should say. It's traveling as a parabola. Also, this would be giving you some kind of average velocity, which is not what we're interested in. These arrows right here, this one, and that one, and that one, these are changing over time. We're not asking for average velocities for these projectile motion problems. We're looking at the velocity at one particular moment. And that would be the Pythagorean theorem, the vector addition of the x velocity at that moment and the y velocity at that moment. So you should never be taking like this massive triangle where you're looking at the total x and the total y and you're finding your velocities that way. You need to look at these. You need to find these two things and then use the Pythagorean theorem. We'll be practicing this and we'll have some example videos. Thanks very much for watching.